Welcome to this first topic of the Demystifying IPv6 course on IPv6 Overview. So IPv6 Overview is just one of many topics in this Demystifying IPv6 course. So what is the significance of these? I'm going to pull up some bullets, one after another, of things that you should get used to looking at. First of all, hexadecimal 86DD. That is the ether type field for IPv6, just as hexadecimal 0800 is the ether type field for IPv4. This is referred to as colon colon. Colon colon implies an all zeros address in the IPv6 addressing scheme. More about that and the format of many other addresses that are following on this slide in the IPv6 addressing topic. Colon colon 1 is actually all zeros ending in 1, which is the IPv6 loopback address, similar to how 127.0.0.1 is the IPv4 loopback address. FE80 colon colon /10, that is the link local address for IPv6. In a way, it's similar to the automatic private IP address that would be configured in the absence of a DHCP server with IPv4. FF00 colon colon /8, that is an IPv6 multicast prefix. 2000 colon colon /3, that is the IPv6 global unicast prefix space. Basically, the block of IPv6 addresses that are being handed out and considered globally unique. Protocol number 58. That is actually the IPv6 next header value for ICMPv6. 3.4 times 10 to the 38th. IPv6 addresses have 128 bits, so 2 to the 128th is equal to a very large number. So essentially that number, 3.4 times 10 to the 38th, is the total number of IPv6 addresses available, as opposed to 4.2 billion as is with IPv4. These 5 RFCs are the base IPv6 protocols. They're the minimum required for an IPv6 implementation. RFC 2460 is the base IPv6 specification, just like RFC 791 is the base IPv4 specification. RFC 2461 is the specification for IPv6 neighbor discovery, which is similar to ARP with IPv4. 2462 is the SLAC, the stateless address auto configuration description for IPv6. RFC 2463 is the specification for ICMP version 6. And RFC 2464 is the specification for carrying IPv6 packets over Ethernet. Anycast is how we refer to an address type that is looking for the closest device to you with that address. CIDR, pronounced CIDR, is referred to as classless interdomain routing, which actually that's the structure, the hierarchical structure now for IPv4. IPv6, on the other hand, is classless by nature. IPv6's default MTU is 1280, as opposed to IPv4's default MTU of only 576 bytes. Next, we're going to look at 10 things about an IPv6 address. Just get you used to looking at them. As you can see, an IPv6 address looks pretty nasty. It's actually in hexadecimal. It's referred to as colon hexadecimal, using hexadecimal digits separated by colons to represent 128 bits, versus how IPv4 does it to represent 32 binary digits using dotted decimal. So the first thing I can tell you about that IPv6 address is it is an IPv6 address. Second of all, it's a global IPv6 address, as per RFC 3587, and I know that because it begins in either a 2 or a 3. It has an implicit structure. Again, we'll talk more about that in the IPv6 addressing topic, but we know that the first half, the top half, 64 bits, are for network, and the bottom half are for host or device, or as IPv6 looks at it, interface. You can assume that its MAC address is embedded in its interface portion, and that's because there's an FFFE in the middle. But be careful about assuming, right? And in general, you could assume that it was his burn-in MAC address. You can assume the network hierarchy, as I described with its implicit structure. It's definitely not a multicast address. It doesn't start in FF. It's also not a link local address. It doesn't start in FE80. It's not an IPv4 address. Okay, maybe I'm stretching to reach 10. There's one thing about it, and that's for sure, it's confusing. So what is IPv6? Well, in a nutshell, it's RFC 2460. But of course there are many others. There's a lot of others. In fact, as the protocol has evolved, as we'll look at in another slide, there's been many iterations, many updates, many strategies or schemes that were conceived but never used, and so on. It's definitely an evolutionary step from IPv4. The idea was take all the good things from IPv4, improve upon them, and get rid of all the bad things too. And so, as we'll see throughout the various topics of this presentation, some of the changes, especially expanding routing and addressing, that was the biggest reason for conceiving of IPv6. But let's go ahead and simplify things. Let's improve things. Let's add more things if we can, such as additional quality of service capabilities, authentication, and privacy capabilities. You might ask, though, what happened to IPv5? There is an RFC that defined IPv5, RFC 1819, the Internet Streaming Protocol. It actually isn't an IP protocol, but they were thinking about using it in conjunction with IP, so they just took the number 5, which was the next protocol in line, after IPv4, of course, but it was never really used. Some of the benefits of IPv6: there's improved scalability, of course, with a large address space, built-in security. There's a lot of things IPv6 refers to as built-in, and we'll see what that actually means. Improved QoS behavior, stateful QoS possibilities using what's called a flow label, similar to the way MPLS could work with an MPLS label forwarding. IPv6 is plug and play by nature. It has, in fact, 2 levels of auto configuration, stateful and stateless, which we'll talk about in the addressing topic. And again, like I said before, it follows all the good practices and rejects the flaws and obsolete items of IPv4. This is a short history of IPv6, short in terms of a summary of items over the years. As you can see here, starting in 1990 was the first worry about running out of IPv4 addresses, and so that led to some predictions that they came up with. In fact, this is the year 2011 where they predicted, after modifying their predictions over the years, originally they thought 2005 we would run out, but now this year we actually have not necessarily run out yet, but as we'll see, we're getting close. There are many other proposals that were analyzed first. The first actual specification was RFC 1883 in 1995, and then an experimental network called the 6-bone began its first production level IPv6 Internet. And as you can see, over the years things have evolved, even to the point to where the 6-bone is now deactivated, and as the last bullet states, as of the 3rd of February in 2011, that is the day that at the IANA, the Internet Assigned Numbers Authority, handed out its last blocks of addresses to the regional internet registries. So it doesn't mean we're out yet, but now it's up to the RIRs, and they're limited on what they have left. Where are we at with deployment today? Well, as you can see, there's a URL which I would suggest that you go to if you really want to get the details. But in a nutshell, we're nowhere and everywhere. And basically what that means is nowhere in terms of there's no ubiquitous IPv6 connectivity from anywhere in the world to any site yet. But as you can see on some of these bullets, there are sites that have been converted. For instance, Google actually uses a different name for their IPv6 site, whereas some of the sites, such as the CAIM, actually uses the same name, and then it's up to your IPv6 stack in your machine to decide, once it resolves www.caim.net to both an A and a quad A record using DNS, which protocol to actually use, IPv6 or IPv4. As you can see, Google, Facebook has also made services available on IPv6. Lots of organizations are considering or have already made some progress in implementing IPv6, as well as there's service providers that have and have not made the change or even plan to make the change to IPv6. One of the big issues with IPv4 is network address translation, which is the main strategy that has been used to extend the useful life of IPv4 to where it is today. But the biggest problem with NAT is that it breaks the golden rule. It modifies data between clients. So if you want true peer-to-peer applications, you have to have a protocol that scales like IPv6 and the number of addresses that are available, so we can assign a native IPv6, or if you want to say a public IPv6 address, to every interface. So global reachability means that every type of device, small and large, whether it's just your refrigerator, a light switch, an actual PC, or a server, has global connectivity using global unique IP addresses, and will even support future applications as well. Earlier I mentioned the idea of built-in functions for IPv6, and this is just talking about IPsec. The biggest issue is with securing communications, they have to be truly end-to-end. So the biggest problem with IPv4 is certain protocols such as ARP did not use IPv4. So it could not be secured by IPsec. Whereas with IPv6, all the different control planes and functions use an IP protocol, ICMPv6, so they can truly be secured end-to-end. And as we'll see when we talk later more about IPv6, it uses actually the same IPv6 protocol specifications, RC2402 and 2406 and 2401. So it's the same mechanisms, but now it also is used to secure IPv6 in an end-to-end manner. So another slide that I'll just build some bullets out as we go along, just making the final comparison of IPv6 versus IPv4. IPv6 obviously has a much larger address space than IPv4. As we'll talk about when we examine the IPv6 header in detail, it has a fixed header length as opposed to IPv4's variable header length, which made processing IPv4 packets by especially intermediate devices, routers, a lot more difficult. IPv6 has efficient hierarchical addressing from the get-go. Of course, IPv4 evolved to that, going from classful to VLSM, variable length subnet mask, to classless, and then finally the implementation of CIDR. But all that, the implementation of CIDR, was engineered into the IPv6 protocol from the beginning. Like I mentioned before, IPv6 has an implicit address structure. So even though it's classless, you can still imply at least what's network and what is interface. Like I mentioned, there's built-in auto configuration. Again, IPv4 evolved to that, mechanisms such as DHCP, but IPv6 has that from the beginning. I mentioned on the previous slide also the built-in security aspects using IPsec. I mentioned earlier that IPv6 also has alternate support for QoS. So what one might refer to as stateless or class of service, using the protocol differentiated services and priority bits today, but also IPv6 supports stateful or integrated services using the flow label, which is an MPLS-like implementation for IPv6. And finally, by default, IPv6 supports bigger packets. So the default MTU of 1280, because IPv6 of course was conceived of and designed at a time when the links were a lot better than they used to be when IPv4 was originally conceived of in the late 70s. So therefore IPv4 had a smaller default MTU. Thank you for taking this time to view the IPv6 overview topic of the Demystifying IPv6 course.